activity of work we'll talk about, which is the conceptual research that you're all being asked to carry out as a team. Each team right now is working on that, and it's primarily being guided by Theo. It's the main topic you check in with Theo on a weekly basis. I'm just gonna get rid of this echo. Sorry, 1 second. Is this better? No. It's way worse. Okay, so we'll stick to this. And then there's a work you're doing with Octavian and Alex at the moment, which is very similar to workshop mode, right? Which is we need to get you skilled on a programming environment, right? So a lot of you, again, I'm super happy. Most of you have either interacted with me and Alex in workshop 1 or workshop 2, and those who haven't worked with Apple or the other workshops, so it's also fine, which is you're already quite skilled on the Maya modeling environment and the Maya simulation environment, right? So 95% of you are coming very well prepared as we usually enter studio. So I think we're in a really good place this year, which we should take advantage of, right? That all of you are familiar with the simulation and modeling environments inside of Maya. And what you're doing with Alex and Octavian is very targeted Unity work. And the reason we chose Unity, I'm sure Alex has talked to you about it with Octavian, is we think Unity is the perfect platform for the studio and the DRL moving forward, because it allows you to do a lot of the basic modeling, simple modeling that you get in Maya, but it has an incredibly powerful programming environment in a very friendly programming language, right? So, I think Octavian is teaching you right now in C#, I believe, within Unity. I don't know, Alex, if that's what you guys are going through, but I think it's C#.
Yeah.
And, a lot of the work you guys have seen in the past would have been through processing in the DRL. And 1 second. And that echo once. So yeah, you would have seen a lot of that work in processing in the DRL, and that was in a very different programming language that was super friendly, and that's why you saw a lot of that work take off, that the students were able to start programming and writing code to produce these fantastic results. And we believe Unity is just as friendly, and we're hoping to see excellent results again this year. We've had students use it in the past, and we've seen some really, really good results. So basically, that's the idea of using that platform. So you have your modeling and your simulation within Maya, and then you can start to have a lot of your programming environment inside Unity. And in the end, we believe we can bring the two very, very close to each other. So the Unity work, think of it like a workshop, right? Me, Alex, and Octavian have a plan for all of you for the next 5 weeks. We're taking you through that plan. A lot of it is focused on you learning to program in C#, learning to program in C# specifically inside Unity, to be introduced to the concepts of object-oriented programming, etc. Right? And these are all super useful skills for you in the DRL, but also specifically if you leave the DRL, once you leave the DRL, C# is an incredibly useful programming language, right? So that's another advantage of working on Unity instead of C++ or processing, because C# works inside Rhino, C# works inside Unity. C# is like, if you ever do anything on the Apple platform, you'll be doing it on C#. C# is the main programming language for Windows-based environments. So you have a lot of flexibility if you learn C# versus any of the other programming languages. And then the third and final element that we'll be working on, stream of work this term, is basically the work you'll be doing with me and Alex, which is on the kind of conceptual computational thinking, right? So how do we bring the two worlds together, right? So you're doing this kind of conceptual research with Theo on the elemental forces, and with me, we'll talk, I'll be joining Theo in a lot more of those tutorials moving forward. And then you're doing a lot of this programming world with Alex and Octavian, which is primarily about concepts of object-oriented programming, rule set-based behavior. So how do we bring those two worlds together? And that's the kind of stuff we'll be discussing in these Saturday sessions, which is we'll be going through the research you're doing in the studio and starting to investigate how we will set up that translation from that research into the programming environment. Now, that doesn't mean we'll actually be doing programming in this session. This will be a lot more of a conceptual session where we'll be looking more at simulation tools inside of Maya, and we'll be looking at your diagramming about how you're diagramming what you're simulating and how you're diagramming what you're finding in the conceptual research, with the aim that, you know, in this term we'll create a bridge between these three activities. So you know, I think term 2 is one of the most exciting terms for the studio, because, you know, it's just the kickoff. We're starting to see where each team can go, where the projects can go. There's not a very straightforward direction because it's the research studios now. So I'm hoping we do a lot of really interesting work. And if you guys perform anywhere at the level that you did in the workshops, I'm pretty sure we'll have a very good start to the year. So not to drag on much longer, it would be good if each team took 5 minutes at this point, and if only one of the people in the team want to talk up, that's also okay. But each team just go through over 5 minutes what they're looking at during the week at the moment, apart from the Unity work. So, you know, I have an idea of what you guys are all working on, and then we'll introduce the other stuff we can start working on in this session. So, you know, we'll go standard team 1, 2, 3, 4. So if just each team wants to take 5 minutes and tell us about what they're researching at the moment. So anyone from team 1 wants to start? Maybe introduce yourselves, like who is team 1, and then just 1 or 2 of you just go through what you're researching at the moment.
Yeah, we are team 1, and Lokai will share his screen.
Yeah, Mustafa, could you please give me,
yes.
Let me to share the screen, yeah.
Yeah, 1 second.
Thank you. Actually, we prepared about half an hour to share our stuff.
Over half an hour.
And, we will cut it. Yeah.
Don't worry. Yeah, you should have access now.
Yeah. Could you all see the screen? Oh, sorry.
Yeah.
From the first one.
Yeah, and we are the Earth team, and our team members are me, Jadon, Lekai, and Zero. And basically, our current research could be next page, please. So our research is divided into 7 parts, which are the concept of the post-Anthropocene, and secondly, the urban ecology, and next, Earth creates life, and next, Earth the material, Earth and the natural phenomena such as gravity and magnetic field, and Earth and the universe, and the Earth and the theory of sphere. So next page, please. So I think we could go through our PowerPoint quickly because there are so many slides. The first chapter is towards the post-Anthropocene, which gives us a background of our project. Okay, next page, please. So we think that when it comes to the word post-Anthropocene, we can look at this book, and it's acknowledging the end of human-centered design and reflects on how to prototype new relationships with emerging architectural projects. Okay. Okay, next page, please. Maybe we could go directly to page 94.
Did you say page 94?
Yeah.
Do you already have more than 94 pages?
Yeah.
Jesus Christ. Okay.
94.
Oh my God. Okay.
So based on our whole research, give us our background and thought about how to prototype from unit to swarm within a time-based system, and using material and force field like bacteria and gravity and magnetic fields. And we could also use many behavior of life, such as board simulation, convex game of life, genetic algorithm, and colony algorithm to do our simulation. And the right diagram could Leka and Siron, could you explain?
Yes. We mainly figure out our project with energy and nature and how we consider our nature as a scenario and context. And meanwhile, nature could also provide the sustainable energy. It will include the transformation between the resource. And meanwhile, the energy between the energy and the project, we mainly want to probably create a strategy which can capture, store, and release our energy into the project. And meanwhile, project will consider with two parts from the bottom to up prototype. One is the unit and another is human. Yeah, more like this. Should we?
Okay.
Yeah.
Yes, and we present three assumptions according to the previous research. And first is the redefinition of the Earth for like forest on the cloud. The second is interstellar assimilation based on the Earth, like the introduction of the Earth's environment in the universe. And the last is self-organizing rejuvenation of the Earth, of the surface, like the self-organizing renewal of aging land. So now we just is what we did. Yes. Thanks.
Okay. So you guys, is it fair to say, like, just as a quick abstraction, you guys are the Earth team?
Yeah.
Is that fair?
Yes.
Okay.
Yes.
So, can you go
Yeah.
back? Let's see. Let's go to page 2 for a second, and then we'll go to page 94. Oh my God.
Okay.
So what's on page 2? Yeah. Okay. Okay, that makes some sense.
It's
Yeah,
the catalog of our research.
Mm-hmm. Yeah, makes sense. Okay, and then if you go back to page 94. Yeah. So obviously, yeah, this is your current conceptual diagram, right? And I guess the question here is, okay, what are we trying to model here? So you have some keywords like unit, swarm, behavior, life, material, force field. So a lot of these things imply very different things. But how do you derive any of this from the concept of you guys being like focused on this idea of like post-Anthropocene? You're focused on Earth. So that because there's a lot of abstractions here. So how do you go from that to this, if you know what I mean?
Yeah. Yes. We think the Earth contain the surface of the Earth and the Earth and the relationship between Earth and universe. So now we just come up with three initial assumptions from the surface of the Earth to the universe, but now we're not sure to modeling something. Look, can you go to the next page? Yes, maybe we can explore more things on the three assumptions or other new assumptions. Maybe we can know what we want to model. Yeah.
Okay, fair enough. Can you go back to 94 for a second? Okay, so yeah, I think this is very different than this, obviously, and I think you guys understand that, right? This is kind of a let's call it, this is kind of a system diagram, right? How you guys are starting to think of the system as this idea of unit and human and how they interact with some sort of cyclical system. So that's quite clear. I think we can hold on that for a second. Then if we look at this here, you have essentially 2 or 3 things going on, right? You have this, which you correctly call behavior of life, right? These are essentially simulations of dynamic environments in reality, right? So whether you're talking about swarming, whether you're talking about the game of life as a simulation of something else, genetic algorithm is kind of different. And then you're saying ant colony behavior. And then you have these things here, which are very different than each other. So, for example, one way to what I'm asking is like, okay, you guys are talking about Earth as the general concept, right? And I know that's very abstract, but then as a computational diagram rule set, you're interested in exploring a whole bunch of things that you just spoken about, but you need to start somewhere in terms of behavior and rule set, right? So what we're looking for is the interaction of behavior plus rule set, right? Or you can say in reality, those two things are the same thing, right? Like rule sets generate behaviors. And the question now for you guys is, okay, what's the next step here? What's this next level? So for example, if you said we're going to take the behavior and rule set to become, let's just erase this. And you said we're going to say we're Earth, and then we're exploring what behavior and rule set we're going to explore. And the word that is critical to us as a team is material. Okay, that starts to go somewhere, right? So then when you say, okay, material, what do you mean by that? One way to look at that is to say, like what you guys said, soil, right? Another way you can look at it is, I don't know, whatever other materials you have, like, you said bacteria and soil, which is the interaction of two materials, right? In reality. So if you look at soil as a simulation environment or a behavioral problem, what about it are we looking to simulate, right? So that's one way we can start the research, right? So the next step here is simulation. Right. So just to make this even clearer for you guys, you have Earth. Let me know if my handwriting is terrible. Right? As your general concept, what you're looking for is an idea of behavior through rule sets. Right? Which is basically a diagram. And you think there's multiple ways to go from Earth to what this behavior and rule set will say. So right now we're saying one way to look at it is material, right? Another way to look at it is this concept of force field, like you guys have written here. So when I look at slide 95, I can see how you're thinking about that. And then the question is, how do these things lead to a simulation that you can start to progress as a team, right? So right now, I think you guys have, well, can you see it or did it disappear? Okay. We're trying to answer this question. We're trying to answer this question by choosing this so that we can get to the simulation. Does that make sense?
Yeah.
So the question is, yeah. So first of all, what do you guys think? Because you might already have an answer, and I just didn't ask you.
Yeah,
actually, we have. You go first.
We do some research on the material.
Okay.
Page. Sorry, I can't remember.
Page 205.
Page 23. Oh, 2022.
Just from the start with the simulation.
Okay.
Start with the. No. I talk about the material. Page.
Yeah.
27. Or page 33.
Yeah, it looks like
27.
27.
About soil. And 37 about case study. Let me see.
Yes, this kind of case study is all about bacteria, and it could convert the energy and the form, and go down to the magnetic field. 41.
It's a little bit delayed. Yeah.
Yes. So here we mainly focus on the gravity and the electrical magnetic, and we think they are the force field from nature. So next, please. Yeah, so it's about magnetic field. We find its theory and principle. It's all about electromagnetic introduction, and it has really a big, huge influence on in the galaxy and for Earth itself, and. We find some case and generate its history about the magnetic.
But
So
this is the forces section, right? This is not necessarily the material part.
Yes. So my question is about how to think it as a material.
Yeah. So if you go up a bit, you had some slides that were more related to materials. So slides 20 something, or maybe 33 actually, if I remember.
About bacteria or just a simulation?
All of that in general. So yeah, from 27 onwards. So go to 28. And by the way, just a quick question. Are you the only team researching this, or are there other teams on the similar topic?
We have different topics.
Okay.
We are the Earth team. Yeah.
Yeah. Okay. Yeah. So, for example, yeah, this is quite clear. Could you go to slide 33 and then we'll just come back to this 28. Was it 33?
Or about do you mean this page about
No,
magnetic?
No. Okay, so look, like if we go, can you go back to slide 27 or whatever that was, the diagram?
Yeah. This page.
28. Yeah, exactly, right. So, for example, you know, you for some reason, but it's fine. There's nothing wrong with that. So you're saying if we go with the material route, right? The material you're looking at is this concept of soil, right? And you're saying, you know, what is soil, right? It's a kind of, there's two ways to look at it, right? One is it's like a host environment for something, right? And you can say, look, the host environment is for bacteria. And the phenomenon we're interested in for bacteria is this concept of like biomass, or this concept of fuel or food production, right? This all makes sense, right? Or you can say soil is a host environment for another force, right? It could be, my pen stopped working. It could be for something like, you know, water or whatever it is, right? So essentially what we're saying is, if you're going with the concept of soil on its own has no forces. Do you agree with that?
Yes.
Yeah.
Right? Like
Yes.
soil alone does nothing. It's just mud, right?
Yeah.
So the question is like, okay, what is interesting about it? What's interesting about it is it's like a host environment, right? So, okay, it's a host environment for what? You seem to be looking at this concept of bacteria, right? So, all right, so soil is the host environment for bacteria. How does bacteria behave in soil, right? And to what end, right? So that's where some of your later research could come in, right? But basically, if we look at it as a computational problem in a very, very abstract setting, you have a host environment, however we choose to represent that computationally for a second, and then you introduce these foreign elements into the host environment, and these foreign elements are the ones that generate simulation forces in the host environment, right? So for example, we're saying the host environment is soil, and I don't know why my pen is drawing doubles. And the introduction of the simulation force is this concept of bacteria, whatever that means, right? So, you know, my basic understanding of bacteria, but you guys are doing the research, is bacteria has a lot of growth forces in it, right? It likes to self-multiply, which is how you get fuel and food production and biomass, right? The primary force in bacteria relative to those three phenomenon is self-replication. Do you agree or understand what I'm saying?
Yes, we understand.
Yeah.
Yes.
Right, like one bacteria likes to become two bacteria, and two bacteria like to become two. This two would like to become this two. Right, there's this concept of self-replication, and that is fine when it happens in the abstract, but when it happens in a host environment, it starts to have a simulation effect on those materials, if you know what I mean, right? So if I can share my screen for a second.
Should I stop sharing?
Yeah, you have to stop.
Yeah, okay.
Okay, can you see the whiteboard?
Yeah.
All right. So I'm just gonna put it in the world that you and Octavian and Alex are discussing for a second, right? And we're jumping ahead here. Alex, you introduced them to the idea of like voxel and particle, right?
Yeah, we were talking about it in the last session.
Okay,
Octavian.
perfect. So you have two computational host environments the guys are teaching you, right? You have the computational host environment of the voxel, right, which is the chessboard. And then you have the computational host environment of the particle, right, which is an unstructured grid of elements. right? And in both of these, we can play out that conversation we were having, right? So you can say this unstructured grid of particles is your material, right? Also known as soil. Or you can say this grid of voxels is your material, also known as soil. Now, the next thing is, okay, you're introducing this simulation force, which we're saying is this concept of bacteria. To the simulation, right? So in the voxel world, it could be just the introduction of bacteria as this kind of basic introduction to the concept of like in the game of life, you're switching on certain cells that start the simulation, and the simulation is based on a rule set of growth. In a particle world, you could introduce a bacteria, like a simulation force, by introducing new particles into the environment that create a disruption in the host environment, right? And what we're saying is that the core dynamics of the bacteria material, let's say, is this concept of self-replication, right? So this is these host environments, this is how they're getting affected by these forces, because these things are self-replicating in whatever pattern, right? So this is just one idea. Like, I don't know what else you can derive from the research that you're doing into these kind of keywords you were looking at, like fuel, food production, and biomass, right? Because those are actually all interactions of how some sort of bacteria behaves, right? So this is how you can easily go from earth to material to a simulation idea being material plus simulation, which is soil plus bacteria, and then you go into one of these two diagrams computationally, right? So that's a very, very clear connection. And based on what you find out at this level of research, we can change the diagram, change the rule sets, and change the simulations, if you know what I mean. So that's one way. That's one way to look at it, right? Another way to look at it is, if you remove the bacteria, what can you do with the concept of material and soil, right? So that's how you have to start thinking about your research, so that we can come with more clear ideas about how to change this into a computational diagram, if that makes sense.
Okay.
And I have a question. Mustafa, you said the material could be bacteria or soil. So I'm wondering that could the material be another thing, such as one bird in the Boyd system, or just an ant in the ant colony. So we could explore more possibility for our simulation.
You could, but I wouldn't call a Boyd or an ant material, because those are active units that have behaviors in themselves, right? A computational material, that's why I'm using the word host environment, right? It's just the host to another behavior, right? So that's the interesting thing about what could be your research computationally to start, which is, you have essentially an inert computational medium, or like a computational host environment that has very little behavior, but then you're introducing this other force or other behavior thing into it, which is the bacteria, which affects it. So I wouldn't call an ant or a Boyd a material, right? Because those are very active forces, and they have their own behavior, versus like just simple particles or simple voxels that are just the host environment. And what's interesting is that obviously, as the research advances, you can start to give this material properties, right? Right now, we're just thinking of it as this blank particle or a blank box, but you can give it properties in the future that make it more hospitable to your secondary forces, or it could make it more not hospitable, whatever the opposite of hospitable is, like lethal or dangerous or not welcoming to that secondary force, right? And so, and then it becomes basically what, if we think of it in the abstract, we're talking about a growth system operating within another medium. And the interesting thing will be, how do we push this forward? Are we concerned with the blue stuff, or are we concerned with the green stuff? Or are we concerned with both? That conversation it's way too early for that. But that's why I think, like, as you're thinking through your research and doing all this research conceptually that you have in your slides, this diagram, how you convert that into a computational model, is super important. And what we'll try to do between me, Alex, and Octavian is help you with that diagram, which is, can we use Maya to kind of push forward some of this diagramming quickly? But in the same time, as you're getting better in the programming environment, we'll be asking you to try to replicate some of that through the code, because that's where you'll have a lot of control and we can push the project forward. So to answer your question directly, yeah, I wouldn't consider that stuff material.
So could I understand the material as an environment that hosts life? Yeah.
Yes. Yeah, exactly.
Right.
Yeah, I think that's the perfect summary for it.
Okay, thank you.
Okay. Does that make sense to the rest of you as a team?
Yeah.
Sorry,
Yes.
Could I ask another question? The game of life actually is not a simulation for real life, but is explore the relationship between a cube and its 8 neighbors. So I was wondering that could we use a game of life as a rule, but we all know that it's not real. It's not in real world. It's not. It doesn't exist in the real world. So
yes,
how could
that's
we?
fine. These abstraction diagrams should not be. You don't have to say it's 100% related to the real world, right? So you're trying, like, for example, how you would apply the game of life rules to this concept is, like I'm saying, like you would look at this diagram, right? So that, bacteria likes to do self-replication. How would you create a self-replicating rule in the game of life? That's how you would think about it, right? So I think, just to be clear for you guys, what I would do next is, first of all, you need to agree that, at least for maybe a week, you look at this diagram. Doesn't mean this is the diagram you're going to take forward, but it's a diagram that you can start with, right? Second of all, you need to be super clear about this section of the diagram, right? And then I think you can say, okay, how does it translate here? And how does it translate in this world, right? And you can explore that using Maya. Even here, obviously, you don't know how to do game of life in Maya, but you can model it, right, by just switching on and off cubes. And in the particle world, a lot of you already know how to use the particles. But I would explore, for the next session, I would clarify this diagram, make sure it makes conceptual sense. It will also help you do a lot more research about this concept of a host environment, a computational host environment that sustains life, like you put it. And what is that environment, and what is that life force? And then how do we model it in this world, and how do we model it in this world, so we can see which one makes more sense, so we can push it forward. Okay, does that make sense?
Yes.
Okay.
Yes.
May I ask one question?
Sure.
The host in the system, is it more like a creature? It needs to be alive. I mean, since it's like a host, so it could be simulation. It can't be a natural phenomenon, or I mean, like physical phenomena.
I think for you guys, it makes sense to think of the host as a material, which is, it's basically a medium, right? It's the thing that something else operates within, right? So, you know, I wouldn't worry about what it is. It's like right now it's an abstract diagram.
Okay.
All right.
Yeah.
Okay, cool. Should we move on to the next team?
Yeah. Yeah.
Okay, thanks, team one. Do you have 200 slides as well, team two?
I think we are team two. Yeah, we have 100 slides exactly. But we will try our best. We will go through them very quickly. Yeah.
Yeah, team one did a good job of that. Yes.
So which screen I'm sharing? I'm sharing the, you see the catalog?
I can see the catalog.
Okay.
So you're the water team.
Yeah, obviously. Yes, we are the water team. We are Yuji, Tyler, Ula, and me. During this week, we tried to focus our research on, sorry, let me minimize that, on five different directions. So we have firstly water as source of life, which is more conceptual, okay, water as material, where we try to go through the different properties. Water as technology, exploring water as technology from ancient infrastructure, contemporary, and some case studies in robotics and very recent studies. And water as environment, studying different populations, and water as geography. And finally, water as threat. And we will try to relate all these together. So I'll go through this part fast. And water as material. Firstly, we went through the chemical composition of water. We saw some special properties and their basic effects, how we realize, how we see these properties happening. Phase changing, some diverse properties throughout the phases. Physical properties that water has. Patterns that we can have from some different behaviors, and how we could finally harvest energy from these water properties, some main ideas. So first of all, the spatial characteristics. I will go through this. I don't think.
Yeah, it's pretty clear. Don't worry.
Yeah. Phase changes. Some other natural behaviors like volume expansion, bending, stickiness, like the different shape, cluster behavior, formation across the different phases. I think, yes, we don't need to focus on that right now. And transparency, buoyancy, which is quite an important property, a physical property, because we can extract a force from that. And yes, then we can go to patterns. These are Ula's photos from the same spot, same beach, same time, but different day. So we can see how different formations of sediments and sand, and then different patterns in water again. So to sum up, how we could extract energy from water, there are some variables that we could study, like which come from topography of the subsurface or the coastline, temperature of water, salinity, acidity, or pH, and then we could see different processes that could help us extract energy, which is erosion and deposition, which are related to the coastline. And we can see some processes that could help us. We could have the extraction of sediments. We was thinking also creation of rocks or crystallizations growth or transportation of sediments simply by deposition. And then from current and waves, we could study different patterns that we get from different types of currents and waves, like tidal currents. And then other processes like vaporization, pressure, turbulence, and growth of microorganisms or algae. Yeah, some ideas here. Hope this is clear. And then we went to water as technology. These are some direct ways of harvesting energy. We have some ancient examples we don't need to talk about this. And we have some direct ways of harvesting energy through dams, reservoirs, and hydropower tools. And then indirect ways of harvesting water with intelligent systems and robotics. We could focus on that probably. Yeah, this is a sum up for the ancient techniques, and then some dam exploration. And then we have some these case studies, like this example from the MIT Self-Assembly Lab, where they used deposition in order and wave energy and ocean currents to grow islands. Then we have this example from MIT lab. Yeah, probably don't play the video, but where the water vapor is used to lift weight, which is 10 times more than the weight of the material. Sorry. Yeah. Anyway. Then we have this example from West Institute at Harvard, where the water pressure is where they're harvesting water energy from water pressure, and they're programming materials to respond to this natural phenomenon. And so from origami techniques, the structural a skeleton is created with a muscle behavior, which can grip, lift, and twist 1,000 times the weight of the object.
At Harvard and MIT created.
Yeah. Then we have some, we could say that we harvest energy from microorganisms like pyrosome with bioluminescence. Again, it's a study from West Institute. And then, sorry. There are some case studies about harvesting energy from algae. Anyway. Sorry, they play on their own. Then water as an environment. Does anyone want to
yeah, so we made some research on different case studies on different settlements around the bodies of water on Earth, and we have a few case studies mostly on lakes and seaports and the ocean. Where the reason why we are looking into these case studies, we wanted to like understand how people can live on water, how they use water as the only resource of life, resource for food, resource for energy, how they use water as a driving force to design their homes, design their transportation. Like some of these case studies show that these dwellings are on stilts because of the water level changes throughout the year. And we've made a comparison in terms of population between these case studies, in terms of lifestyle, in terms of the challenges that they face, and in terms of how the different typologies that they have as homes. Like some of them live in boats because they found it convenient to live on boats rather than on homes on stilts. Some of them created islands made of reeds, artificial islands made of reeds, because they realized that the environment there, since there is a constant flow of water, and with these islands being on reeds, they're capable of living without any challenges of, for example, erosion or these kind of stuff. And then there are others who live in the middle of the ocean, again with the houses on stilts. This is the kind of typology that these days exists on water. And then there are different challenges they face, from health challenges, flood challenges, the quality of water, the pollution. And from these, we would be able to derive what is the optimum way to have a living settlement on water.
Yeah, then we studied the water as threat with water scarcity, sea level rise, floodings, and erosion. And these are some topics that we could also address. So we would like to address. So, for example, erosion is with the sea level rise. It seems like we have an erosion threat of disappearing cliffs, and a thought could be like, what if we could, instead of stopping this, instead of trying to control this wave energy, these waves by building walls or just by building breakwaters, what if we could harvest energy and also protect the coastline from the erosion? So yeah, that was a bit briefly our thoughts and research through this week. I hope it was clear and fast.
Yeah, I'll speak to you.
Before we will move on, I'll just like make a small comment, which I'm sure will apply to air and fire teams as well. I think all of you are working with high-level concepts because obviously these four elementals can be interpreted in 1,000 ways. And it would be really useful for you, I think, in the next stage perhaps to allow for more specificity, because in each of the presentations so far, I think there's like 1,000 projects in each, because they can tackle so many different ways in which you can observe your respective elemental. So I think like this was a really good initial step towards really expanding the definition of what water, air, earth, or fire might be. But I think for you in the future, it will be so much easier to kind of try to create a bit more specificity, at least in the area that you wish to explore, because I find it unlikely that you will be able to take, let's say, these 5 chapters and weave one common thread through each of the topics for like one topic per chapter in order to create a project. I think it's more likely that picking one of the concepts within each of the 5 chapters will actually restructure the rest of the chapters into something that needs to become in order for you to start dealing with a certain issue.
Yeah, definitely.
And by issue, I don't mean like you need to like pick, a disaster or something like that, like issue as in concept.
Yeah, it was just in terms, it was our first week research.
Yeah. No, I understand.
Yeah, I think it was a.
Yeah, we agree.
Sorry, go ahead.
We wanted to, internet is slow. We wanted to touch on all aspects of water, and mainly not only the disasters part, but also like how the indigenous people live actually, and like so that when we framework our. Sorry, Mustafa.
No,
Yeah,
I
I think
understand. I agree. It's like it's a very good way to kind of relax the definition of the elemental.
yeah, I think it was like a very clear overview of what it can become, right? So, if I just summarize everything you guys said, and maybe small changes, I'm not sure. So, okay, your main headline. So the last theme was Earth. Your main headline right now is water, right? You kind of split it in 3 or 4 directions, I would say. I would say one is water as a force / material, water as an environment, and perhaps the one I understood the least. Like I understood, but it's hard to consider it a category necessarily, is what you were calling water as a technology. That one is the most confusing. So then under water as a force or material, you had things like, I think, erosion was something you talked about. You had something like deposition was something you talked about. And I'm sure there was more. Water as an environment, you looked at it in very different ways, which was interesting. You can look at it as an environment for something like salt growth. You can look at it as an environment for something like reef growth. You can look at it as an environment, interestingly, for humanity, right? So settlements, which is very abstract. By definition, you have environment as for pollution. Then you had this technology section, which you kind of talked about, like essentially managing water, right? Like whether through aqueducts or routing or whatever that is, or essentially harvesting the energy of water.
Mm-hmm.
That's how I understood your presentation today. So I don't know if that's very different than how you saw it, but that's kind of how I saw it. And yeah, to Alex's point, there's very many different research opportunities in each of these directions. So the question is, okay, you guys have done a lot of work here. How do we take the next meaningful step for you guys to progress your computational diagrams, right? So each of these, interestingly, can become a very different computational diagram as a concept, right? Like this, literally all of these can become very different computational diagrams. So I guess we need to try to there's 2 options here for you guys right now. And, this could change over time. But right now, there's 2 different options. You choose a strand and that we focus on. I don't know if that's the most helpful way to do it. Or we try to say, can we abstract some of these things into a higher level diagram that we explore? Which I'm not sure how we would do that.
I actually think that the green section of the diagram is actually quite helpful. Like force environment technology can still play a part, whichever of the points in red you choose. So if you, I don't know, choose harvesting, for example, yes, technologically harvesting might relate to food production or energy harvesting, but it also requires a certain type of an environment, and it also requires a certain type of force or material. So what I meant by like choosing one red concept restructures what happens in the green tier, I think applies. So any of these like end concepts will sort of reinform what becomes the new red branch for the green concepts, I think. And I think that can really easily guide how you think about your computational model from now on.
Sure, that's another way. That is one way to look at it. Like, for example, I think something all of you will have to face, because it's just general computation, is you need to select a meaningful host environment for your phenomenon, right? And you can think of water in various ways in terms of a host phenomenon, right? Like you can have free-flowing particles, right? That's one way to do it. The more computationally familiar way might be the concept of a vector field, right? So this is literally like just simple fluid dynamics. Yeah. Which is the kind of host environment for whatever forces you put in, right? And then So there's a choice of medium to decide, like, what, to Alex's point, how we abstract the concept of a water-based environment, right? I'm not sure that voxels could be the right way in this project, though it could be interesting to think about that. Is there a way to represent your project in a voxel fashion? I think it's more realistically a field fashion would be the correct interpretation of your project. And then, depending on these kind of decisions you make, it has very different implications on how it interacts with this environment, if that makes sense. So in a big way for you guys, the next step computationally is probably to focus on the environment concept of the water, right? Because I don't see a route forward for you computationally where you don't have to address that question. I think it's fundamental that you have to explore the concept of how do we abstract a water as an environment, right? And like I'm saying, I think it's either kind of this particle population or this kind of force field or field interpretation or diagram. Yeah, but yeah, I don't think the right thing to do is jump immediately ahead to that, right? Because you used words like turbulence and stuff. Like, what is turbulence? You know what I mean? Turbulence is the disruption due to the force in a medium, right? Or in the environment. So the question comes back again, like, for example, if we look at turbulence in a normal fluid field, right? Like, let's say that's an undisrupted fluid field. Turbulence is just you coming in and introducing a certain disruption into that field, right? That is turbulence. So my point is you need to think like 6 steps below where you are currently thinking, which is like, okay, what is the computational diagram that allows us to work through these ideas, right? So you're talking about, okay, the human settlement and how the human settlements respond to the flow of water and the turbulences of water. My question is like, okay, what is flows of water and turbulences of water? And then we're like, okay, those are phenomenon of water as an environment. Okay, how will you represent that environment computationally? Then you don't have many choices. One way to do it is you ignore that question completely, which we saw last year, for example, right? So if you guys remember Theo Studio, the disaster team who were doing the migrants, they didn't have this problem at all. They completely ignored this question, and they just did a simulation of dots that represented boats. But I don't think that's what we want to do, because we're not focused on the boats this year. We're focused on the elemental forces. So you're saying, okay, then you have to represent this concept of water as an environment. And that could be this kind of loose population of particles, or it could be the concept of a field as the initial host environment. So again, if you talk about it as a particle population, there's different ways to talk about turbulence. If you talk about it as a host field, there's very different ways to talk about it as a population and how other systems inhabit that environment, right? So very similar to what we were talking about with the soil team. So I think it's unescapable for you guys as a team to think about the first meaningful question for you is how do we computationally abstract water as an environment? I think that is necessarily the question we have to ask as a team to start your computational project. So we should look at the computational models that exist currently to simulate water-based environments. That's one piece of research. And the other one is like, okay, what can we get our hands on very quickly? That will be a lot of the tools we have in Maya. And then the next step will be, how do we diagram those so we can start to think about introducing them in a code-based environment, which is in the environment Octavian and Alex are teaching you, is either some sort of grid-based voxel or some sort of particle-based field that you program, right? And depending on what you guys do in the next 2 weeks, I think the answer will be clearer along that direction. But I think, yeah, for you guys, it's super clear. We have to explore what it means to computationally diagram water as an environment. The only thing that might not apply to that is the concept of water as a technology, right? Because in the sense there, water is the secondary medium, and it's operating in something else. So I would say we have to be aware that that might be the only exception to this diagram. But everything else you talked about today, I think how does water operate as an environment is the right place to start. You know, whether it's deposition, whether it's erosion, whether it's salt deposition, whether it's reef growth, whether it's human settlements on the water, whether it's you know, all of those concepts. I think the right place to start is this. Does that make sense?
Yeah. Can I ask a question?
Mm-hmm.
So about the simulation, because computational wise, we need to think about how to simulate the such as water's behavior, right? And then how can we turn this into a project to develop like later step?
God knows, right? Like we have a year. This is honestly, like in studio, it's so different than the workshops. I'm confident we'll do it. Like we've never not done it, right? So we always figure a way out, and it's, you know, that it's usually interesting. Like maybe 4 weeks from now, you'll come up with something that gives us that first idea. But you know, right now we're all essentially researching together, right? I just know a bit more than you. I'm a couple of steps ahead of you, and I can help you organize your thoughts. But at this point, it's very different than a workshop, right? I don't know where this can end up. Like when we do workshops, me and Alex know where we want you to get to, more or less. But in a studio, it's open, right? Maybe from a year from now, we'll be talking about how water navigates through a building. Therefore, how do we organize the building, right? As a kind of water management system for energy generation. And that could be something that comes from this research. Or it could be how we develop a kind of robotic system that navigates these water-based environments for the purposes of harvesting that water. Or it could be how do we generate these kind of dynamic settlements that occupy the water base. All of those concepts start from this point, right? But we don't know. And the idea is that it's a studio, so we'll figure it out as we go along with you guys. And you know, you could see in each of those three concepts different parts of or for example, like how do we build a self-growing architecture in the water-based environments, right? That would be more similar to the coral reef salt ideas. You know, and we won't literally build them out of salt, but we would have abstracted the principles, or maybe we would build them out of salt, right? We don't know. But that's what's exciting about the studio. Like you guys are doing good research now, and we're trying to help you abstract it so we can build the first computational model. And then the conversation opens up because we start to think about, you know, as the studio progresses, okay, how do we turn this into tectonics? How do we turn this into organizational principles? How do we turn this into physical stuff, right? Geometry. And that's when it gets interesting from the project perspective. Right now, we're trying to find your base research for the studio.
Okay, thanks.
I think maybe circle back a little bit to the sessions that we did in first term regarding like fluids in Maya with the dynamics. There was one session for that and some on the particles. And I think somewhere between those computational models in Maya, you can develop something for yourself that might be applicable to your project now, which, like Mustafa said, will eventually evolve into a diagram that will evolve into a computational model that will find a home in Unity.
So yeah, if you guys did these simulations in Maya last term, I would definitely encourage you to go open up those recordings, and that's a great place to start, as well as doing your Google research about those things as well.
Yeah, because I think like most of the sessions that we did, and I'm talking not about the workshop-specific sessions, but
We're talking about the general.
Exactly. Like they were focusing on Maya dynamics in particular. So it was encloth, particles, and fluids, which roughly can translate to encloth can even be somehow interpreted as air because we had inflation tests. Fluids definitely can be interpreted as either water or air, and particles work again with both fluids. I think maybe Earth is the one that might be closer to the particle work that was done in workshop 2 because there were a lot of attempts at creating growth systems and also interaction between one substrate and another, meaning two sets of particles in which you can, like we were saying in the soil team, if you're thinking it of as a substrate or that occupies another substrate in an environment, then you can think of it as like two, colonies of particles inside.
First step would be to go through the fluid simulation and to study this part. And
It's the obvious thing to do, yeah.
Should we study how to create? I think different patterns that can be created from fluid or different from different forces, and I don't know. Should we be concerned with how fluids interact with a force, or just to focus on fluids for the beginning?
So we're starting with the concept of fluids as an environment. So you're interacting just with that. But then, yeah, if you start to add other forces, you start to add other materials. Yeah, you're moving into different territories. So I think first let's just get comfortable with very quickly with the general basic computational diagram with fluid as an environment. I don't think that'll take very long at all.
Which is essentially what CFD is. Like once you create a container for Maya fluids, that's already your environment that's based on a fluid dynamics model.
And then the next step, depending on where you are, could be, okay, if we explore deposition, how would we do that computationally, right? Then you'd have to introduce a particle population into the CFD model and allow them to somehow deposit. If you were talking about erosion, it would be a very different model because you might have a particle field that the fluid dynamics model starts to erode. If you're talking about growth, it's a growth system being affected by the CFD. So it's very, very, very different. If we're talking about harvesting, you would introduce maybe more rigid body physics in there and get them to do certain things in the field. So there's very different directions, which is why I'm saying let's get familiar with the concept of water-based simulations, both in terms of computational fluid dynamics in Maya, but also the research you guys do as you've been doing from Google. Like, what do people do with this kind of stuff? What is the cutting-edge research here? What are some ideas we can look at in terms of this concept of fluid-based, water-based environment simulations? Okay. Cool. Should we move on to team 3?
Yeah.
Thanks. So team 3, what are you guys, air or?
Air.
You're air. Well, so what's the last team? Is it fire?
Water.
Sorry?
Yeah.
So there's earth, water, air, and fire we have not seen fire yet.
Yeah, so the last one is going to be fire, right? Is that right? Okay.
Yes.
Okay, so this is air.
Hello, everyone. Our team is the IFS team, and the members are Yu, Gojak, and me, and Xiaoren. We have done the research on the topic into 4 parts: the cultural implications of air, and the different disciplines it involves, the way it is used, and some scenarios that we feel we can study at present. Next, please. Next. Air played an important role in many of the world ancient cultures, which is one of the basic elements of the world. Next, please. and it is one of the substances we deal with most frequently. It takes many forms, like gases, winds, and clouds for mirage, weather, and climate, smiles, breathing. Next.
Yeah, so first of all, we research some related disciplines, and the first is the physics, and we research some basic properties and some optical properties related because for example there are some phenomenon, and after that, we research the air in chemistry, and first we research the major constituent, and then something about noble gases, and after that is something about biology, like cellular respiration and photosynthesis, and then is something about geography, like atmospheric circulation and typhoon and hurricane. And the last is air in psychology, and is something about things. For example, some people will buy the air because air has some relate with emotional memories.
Next page, please. Here are several kinds of air structures we have studied. We may inspired by several of them. Next page, please. In the first part, we want to talk about air's body structures, air beam structures, air cell structures, and so on. And each of them, we have several interesting cases. We think the first one, the fifth one, the buoyant and lighter than air structure may be the most interesting part because it harvests the solar energy to heat the air internal. Which can keep the structure floating freely and gives many opportunities. Just go through this quickly.
Yeah, that's fine.
Okay. In the second part, we think air can also be used for movement, like pneumatic building skin, air muscles, and air springs. And in the pneumatic skin part, the artists also use solar energy to heat the internal air of each small fabric structures to form a breathable dynamic shading. When these small parts go together as a functional skin, which can be a way of machine reacting to the environment. Next page, please. Okay. Besides, the air structures also being used to create fixtures and some materials with added air, like metal foam, which we think the feature of strong but light may be useful later. Next page, please.
Hello. And next we will look at some program about the air. Next page. Please go through it and to the forest. Yes. Yes, we know that we are facing a lot of problem with air in our world. Next page. So So the first direction, we want to build an emergency building that could be used in the event of forest fire. This kind of building is invisible in the peacetime, but it can play a role in fire. Its main function is to serve as a platform to set up firefighting while protecting firefighters and also removing some animals as well as the plant from the forest. Next page. And the next topic is about the haze. In my opinion, the haze is a kind of urban disease. And also, there is not much haze in the city, but it actually affects every resident in the city. So we hope to build a floating and mobile building in the sky by using air as a boundary and feeling of the building. We want to deal with the problem of the public activity in the urban city while the haze is coming. So we think that the building that deal with the haze needs to meet two major functions: the public activity and shelter. So because the city activity is uncertainty, so it's the best way to change from single unit to the population to a certain degree, and the basic behavior of the unit are maybe they can move and fall and spread out and also gather. Yeah, that's all.
Okay, so you guys basically, it's clear, like you're the air team. So now, similar question to the other teams, right? So how do we go from air to the next step of the diagram? So I think the easiest start for you guys as a team from a computational model, it's clear that you guys want to use air as a kind of combination of a medium and a force. I don't think you guys are a team that needs to explore air as an environment to start. It doesn't seem like a lot of your research is focused on that right now. I think we can really look at exploring air as a force for you guys as a team. If you go up earlier in your presentation, somewhere around slides 15 and 20, that area of the presentation. Keep going back. Or maybe actually later. So what's after slide 22? Okay, so with this kind of research, it's obvious that the easiest way to start is kind of inflation studies. What I'm trying to think of is like, how do inflation studies get translated into computational diagrams that can effectively assist you when you move into an environment like Unity? That's what I'm trying to think of, and I don't have such a clear answer to. I don't know, Alex, if you have any thoughts on that.
I think any kind of like structured deployment could be interesting, of like sequence of inflations that is necessary in order to deploy something in a particular manner, because that's something that you could only keyframe perhaps in Maya, but there would not be like a generative strategy behind it in order to achieve it. So if that can be somehow paired with Unity, I think that would be interesting.
Then, so where would they start the research now?
I would start now with doing basic inflation tests on different mesh topologies, because obviously all of these examples, they carry with them a different kind of compartment-based systems. So compartments are something that you might be able to think about as well, like maybe a total amount of inflation that can exist inside one body, so where compartments can maybe even exchange the volume of air. Or just more in the sense of creating deformation in how the inflation guides a certain topological outset. So I think, like, obviously all of these, I think you already see that there is a relationship between, you know, the actual container that's being inflated and the air that's being pushed into it. So those will play a part in how your bodies, whatever, let's call them bodies for now, will respond to air inflation. I think that's something that this Maya is certainly very friendly towards.
Okay, so basically, I think what Alex is talking about is like exploring. Can I share my screen? Or, yeah, thank you. You know, simple inflation studies, right? Like the most simple one is something like this, right? Like you have a generic geometry like this. You introduce a source of inflation, it kind of inflates. You know, it inflates into this condition. That's the simplest interpretation of this. And then this idea of like topologically you have chambers, which is, you know, this inflates first, and then, you know, and then eventually these other things inflate. And then there's the concept of, you know, how these things share the air, and how you can pass air from one chamber to another. So again, like, I guess what you're talking about is computationally the sequencing of this kind of inflation study. You know, so that's one way for you guys to progress. It's very similar to the middle section of your presentation, where the research, the translation right now will be air, and then it's air as inflation, right? And then the next step you're taking now are these kind of geometry topology studies and how they relate to inflation. And then, you know, we would look at sequencing.
And another strand of research can also be materiality, because not all materials will respond in the same way to inflation. And that's also something that you can program in Maya, right? Like you can program stretch, for example, like resistance and stuff. And also you could think about buoyancy as well, because you talked about lighter than air architectures. There are certain ways in which you can create buoyancy in a dynamic object in Maya as well, which takes into account the fact that, you know, it also has lift. It doesn't only inflate.
Okay, so let's just think about this for a second. So yeah, we talked about air as inflation. You know, which has a geometry. What's going on? A geometry principle to it. Computationally, you have sequencing. You have materiality. Right, and then you have forces like buoyancy. Is there any other big headline for air? I guess there is air as an environment, but I don't think it's right for you guys right now, right? Because you can also use things like fluid dynamics to simulate air environments, but I didn't see any of that in your research at the moment. I saw a lot of the inflation work, although the haze stuff
could be.
It could be, but you know, I think it'll be very similar to what the other teams are researching anyway. So we can see what those guys come up with first. So I think for you guys, the opportunity here is the inflation work for your simulation, if that makes sense, more than anything else right now. Yeah,
and certainly like topological studies are something that, I mean, by now you already know how to model in Maya. So topological studies are something that you can do very quickly. And then the inflation becomes like an extension of that geometrical study. And then we can also bring in materiality and sequencing into the equation as you progress that. So in many ways, it's very similar to the first workshop, I would say.
I have a question.
Yeah.
Can we calculate in Maya the volume expansion caused by the heat of the air? Or
Yeah, we can by checking things like the volume of the object, pre and post simulation, right?
Yeah.
Yeah. Okay. Thank you.
Yeah. So that's like your question is, how you generate the inflation, right? So one way is to do it more controllably or more parametrically, and that's you can do it by, either just introducing an inflation parameter in Maya, or you can think of it, as the introduction of heat, which means the expansion of the volume of the air inside the object, which leads to a certain amount of deformation in the geometry or inflation in the geometry.
And buoyancy.
And that's also how buoyancy can also work, right? So that's still all part of the inflation study.
Yeah.
Right. And like thinking about that more as a variable set rather than just the geometric output is how we'll probably move it into a more programming based environment, which should help a lot of that stuff there. Okay. Do you guys have any questions?
No.
Okay. Yeah, I think this is probably I think it's the right way to move forward for you guys, because the other two teams are looking at the environment in a very different way. Let's see what the fire guys do, but definitely for air, this seems like the right thing to do.
Okay.
All right, cool. Should we move to team 4?
Yeah.
Thank you.
Okay, let me share my screen.
So you guys are fire.
Yes, we're fire. Okay, so we're gonna also go quickly through everything.
Yeah, sure.
So my fellow teammates are Huiying and Yunpeng. Basically, we started researching a lot about the history of fire and many general stuff, which I'm not going to focus on now. So fire, we all know that is a process in which substances combine chemically with oxygen from the air and they release light, heat, and smoke. We did a bit of research on the different use of fire. So it could be used as a source of light, heat. It was used for hunting in the old days and for automated movement, manufacture, electricity, cooking, glass production, communication. And it's also a symbol in many religious rituals and socializing rituals nowadays. And these are the stages of combustion and the different ways that we can achieve the extinction of fire by smothering, cooling, and starvation. And basically what we wanted to focus on more are the different forms of fire. So fire can also be thought of as heat, as energy, as light. So we researched a bit some different case studies that we thought are interesting for us to get an idea of what a project later could be. So, Huiying, you want to talk about that?
Yeah. And the first part is about the temperature, and we found the we searched for the flaming of the combustion, and we use the high temperature and to search something about the disinfect. And next, and this part is about the temperature of body. And we found something about the human temperature. And next. and some material from that prevents heat from escaping. And next. And next part is about the heat, and we focus the heat transmission. It's about the conduction and convection and radiation. And next. And the heat exchange medium, the refrigerator, and talk about how the refrigerator worked. And next. And next part is about the space heat removal. And this part is about the heat, how to form the fire, and it's a way to produce the heat and the friction. And next, this part is about the convection and how the heat transform, and this is related to the thermal science, and it's a case study to talk about this. And next. This part is about the radiation from the light, and this case is related to the three kind of space, and they formed with the different colors, and the different colors to will influence the human behavior. And next. And next week focused on the heating system, and we talk about the traditional way how to control the central heating system and how to use the smoke of the combustion. Next. And this is the modern way to talk about the central heating system. It's about to use the hot air, hot water, and steam. Next. And this part is about to use the hot air to control the hot air balloon, and it's related to the buoyancy. And next is about the fireworks and rocket. And this part talk about the ingredients of the fireworks and how to control the fireworks work. And it's related to the height, size, shape, and color, and how to use the burst charge to control the fireworks. And the flame test is about the color of the fireworks. Next. And this is a case study to talk about the shape of the fireworks and different ways to fire. And next. And this part is to talk about the principles of the rocket and how the staged combustion cycle work in the rocket. Next. And this part is about the thermodynamics, and we find that we search something about the entropy and the system models from the thermodynamics, and it's related to the molecule, how to the move of the molecule, and a book named What is Life? It's a physics write the book, and he talked about the living cell. And next. And next. And this part is about life.